You have a Zoom, right?
Yes, I sent you a link.
Yeah, I will disconnect.
I just sit down anymore.
There is enough chairs, right?
It's okay. After he logs in, I'll just
Okay, any comments on projects? What's tickling in people's minds? Just speak out loud. Remember, if you don't recruit other people, then people alone. So, that's any ideas?
Yeah,
go for it.
Possible idea is that you hear me talk about coral bleaching every class, but
You know you see the post I sent?
no, that's what I'm saying.
Yeah, Discord. How many of you are logging in on Discord? Okay, I'm putting all my good stuff in Discord from now onward, so you're forced to look at it. One of the largest.
Yeah, 84% largest.
84% largest report of bleach event.
It's very timely, unfortunately.
Okay,
so what I've been looking at is, can you recover bleached corals by touching up to healthy corals? Fairly simple, but seemingly no one has done it yet. Already getting some really exciting results that a healthy coral can recover bleached coral just through physical contact. However, it's not exactly sustainable to have a healthy coral. You have to fragment it up and put it out in the field. So the question is, could we colonize certain materials with the symbionts that are living in the coral, that then you can actually take it and move it into the field? There's this new thing on main campus that seems kind of slightly futuristic called 3D bioprinting. Rather than 3D plastic, the filament you can make into a hydrogel. And then you put microbes in the hydrogel. You can print it out and make it into a mold. Like kind of like a 2D shape. And the question I had was, could we possibly 3D bioprint hydro fused with zooxanthellae that we could stick onto corals that have zooxanthellae then diffuse out and recover the corals? Debbie Ho, who's in this class, also is working with Professor Skylar Scott, who does 3D bioprinting, with the hydrogels. And if we could possibly look into 3D printing this out.
Yeah.
The problem is we'd have to isolate the symbionts from the corals, which is not exactly straightforward. In the class with detail, but it'd be a fun thing to embark on further. And lastly, corals would not be necessarily the only thing we can do with microbes. I think there's a huge application of microbes in the ocean for probiotics, for breaking down plastics, for growing other organisms. It's really interesting to see if could we, even if not correlated, could we get some microbes infused in hydrogels that we could apply on the ocean, whether in a tank or on the field, that have some application for probiotics or recovering healthy or unhealthy organisms.
So a couple comments. Sort of broadening out is super useful, but at that same time, it's kind of nice to start with one very specific thing and then knowing very well that as a technology platform, it would actually be very useful. The second comment is really around, I think one of the important threads to think is from a point of view of scale and frugality and the degree what it's needed. The world of 3D printing and the world of 3D printing in organs has really been much more on a, it's grown, it's sort of keeps getting more and more sophisticated and more out of access in many ways. So I've kind of felt a little bit that organ printing is not there yet from a point of view of mass scale is needed. But there is a massive number of technologies, and just broadly speaking, if all we care about is embedding things in gels and threads, actually start it. What I'm trying to say is think of the problem, but don't hone in on a particular method as yet. Just embedding gels is a great place to start. We as a lab have a platform right now where we just embed in little beads for a totally different reason, because we're doing imaging and sequencing at the same time. So we can image something out at sea, and Enrico was at sea. So these are sort of bulk emulsification methods that we're developing, kind of think of tiny little beads, but every bead has a cell. And maybe I'll show you guys a picture as a second. So the reason I'm just mentioning this is just as a beginning of the class, I'm just kind of holding people's feet on fire about projects and hoping that you all have started thinking about projects. So if not, this is the time. And often every class we will start by maybe discussing a tiny bit on people's projects. And so Danny just started a conversation about Coral, and this is what I want to show you guys. This is what we did out on a boat. So these are all kinds of gels and different sets of materials associated with encapsulation as methods. But one of the things that I'm thinking a little bit about would be set up as project. The most important thing first is to set up your test space. So whenever you're thinking, how would you test an idea? And so the first thing to do is choose a species of coral, which I'm assuming you already have. Find a spot in Hopkins where we rub shoulders to say, hey, can we get a tank? It's super easy for us to get a tank. If you can't get it, then ask me. We'll set that up. Then have a certain set of a scenario where, oh, can I actually bleach a coral so that we know the adoption rate that's associated with it? It's a test bed, so whether this works or 1,000 other things work. Ian in the lab, who's also a TA, Ian and I have done work on how coral larvae pick up symbionts. And so that paper is going to be out soon. And what we discovered is actually coral larvae seek out symbionts. So it's a sort of a process that's occurring. And in that process, we have actually isolated all kinds of breaking the tissue, and it's not so scalable if you're going to take healthy coral and mush it up to get so you need the first thing to even take a step back is about what does culturing actually look like. And so we will next class, I think I'm realizing we're going to discover a framework which we call Fred Park, which is a very broad framework about how do you go about designing a project, your functional requirements, how do you describe all your strategies, and the purpose is as many number of strategies as possible, not just one. While, of course, when we have an idea, when we get excited about something, we often say, we want to start with something. You don't have to start with something, it's fair. But broaden, it's a little bit like a funnel. You broaden as much as possible, and then you narrow out by writing kinds of risks and other factors. And then thinking a little bit about what would allow you to make those decisions. And that requires setting up a kind of a platform to say, oh, this is the only way. And I think in this scenario, the biology is so complex, I cannot imagine any other way but to actually having a coral species to test. So that's just a few sets of threads. This is super exciting. If nobody else, Ian would definitely, I'll recruit him to engage with you. Hannah in the lab is ramping up on the droplet side of the story, so that would be really fun. We've been thinking about it much more from a perspective of analysis, and then of course the materials is what you want to borrow from the 3D printing community. I wouldn't as yet go I don't think structure is playing a role. I think the challenge to think about what does contact actually mean, and there is a amount of literature in coral species in the immune system. So it turns out if some of you have seen those BBC videos of two corals sitting right next to each other, they fight and they kill each other. So if two different species in the contact point, they will essentially start protruding, they generate these all kinds of processes. So you can imagine that there is an immune, and in that process, you get adoption and takeover. Again, imaging is going to be a super important part of it. And next class, we're going to cover some of the squid platforms on the imaging side. So you want to ramp up to build your test system, not even knowing what is going to work.
Mhm.
Because what that gives you a really high solid bar to say, oh, I now know what works and then I can test as many number of strategies.
Yeah.
So this was kind of a quick discussion. Ian, Debbie, go ahead.
Oh, yes. Hi. Can you hear me? Can everyone hear me?
Oh, Debbie, you're muted.
Oh,
No,
really?
I was muted. Go ahead.
Okay, great. I just wanted to add to Danny. So I'm very excited to work with him. We've talked offline about this. So to add to your conversation, I actually do come from the 3D bioprinting community. And I have a lot of experience growing things in bioreactors and printing them, working with materials. And actually now I'm rotating with David Relman, who does a lot of ocean microbiome stuff.
I remember his dolphin papers.
Correct. Yes, yes, yes. So he has a lot of collaborations with marine centers as well. And I was thinking that I could work with Danny on this part. And I agree with you, Manu, that we don't necessarily have to print something complex. But I wanted to add to the frugal aspect. So I don't know if you know, Mark Schuyler Scott has published his work on a low-cost bioprinter.
Yeah,
So
no, I've seen that actually. We did that
yeah, yeah.
last year as a class together. Yeah. No, I think
Oh,
all I have to say is that word is used in a lot of spectrum. Think of the frugal side of that spectrum. That's kind of what's going to get industrialized and used, while there is another version of it that's really for patients. And it has to be that way because just what we are trying to make a heart is a whole another. When you start exploring those sets as a technology, this is reacting to your comment about how much time does it take. And I want you guys to think very differently. It's not about, oh, we don't have the time. No, if your life depends on it, go solve the problem now. And that's what we do on a boat. When we are there, you have something, you have to solve it, you have to solve it now. This is sort of ready, fire, aim. Fire and aim. That's what we're going to do in the class. That's how things work. Is you have to think about something, you have a big idea, you want to start building certain sets of things. So all I'm trying to say is I want this to be in a rapid scale when you're thinking about this. Rule out lots and lots of ideas very, very quickly. And then when something kind of gives you that hint and you've built that intuition, then you build the framework. Say, oh, now we're going to do this. Because it's very easy for all of us to convince ourselves that the largest sets of problems that we will all choose are totally not solvable. We don't have the time. By the way, you guys are doing this all part-time. You all have other jobs, which is you're in research labs and everything. And so just carve that time. And of course, something comes out of it. So that's sort of the primary attitude. Debbie, the big thing that you should really dig in is materials. That's what we should borrow first from that community. Compatible materials with salts. We had when we just did this set of a assay, surfactants that are viable, that work in marine conditions was a huge issue. And so we had to do a massive screening for different surfactants to be able to arrive at something that doesn't completely crap out. Okay, that was really wonderful. I'm pleased there is going to be one project, but none of you are getting off the hook. So anybody has any ideas? What do you guys want to do? Yes.
Yeah.
And again, this is vague. You're not making a commitment yet. We will force people's hand at some point of time. You'll be part of a team. You'll have to but this is a fun time to pitch because it gives people a sense of you might be able to recruit people. Yes. What was your name again?
I'm Jack.
Jack. Okay, so Jack is talking about an idea that he's excited about.
A vein of vague descriptions of things that we
Yes.
want to think about. I think sometimes about this problem of how to get students broadly excited about particular things. And I think a lot about plants, and I have some experience trying to get people excited about plants. And there's this thing
Only if plants could dance.
Yeah, there you go. There's this thing where if you're teaching kids, there are some things that it's really easy to get them excited about and some things where it's a little harder. Often hard is plants. But what's very easy is bugs. It's super easy to get kids super revved up about bugs because they're all crawling around, they're moving. And I think about this problem of it's essentially, I mean, I don't pretend to know a ton about pedagogy, a ton about what's actually going on in the mind. But it's essentially, this is something that's acting on the same scale that you're thinking. This is something that's moving around, it's going, it's eating, it's performing this act on the same scale that you think we're
Time
doing,
scales.
which is
Yeah.
in significant contrast to plants. You're looking at a plant that is something, from your perspective, static. But how do you get people to think about plants as sort of these actors? Obviously, when we start thinking about at a biosphere scale, it's quite important. Plants are actors. They're doing photosynthesis, sequestering carbon, releasing oxygen, all these different things. Essentially, half of photosynthesis when we've been talking about the oceans here is these terrestrial plants. So how do you get people sort of excited about plants in that way from a frugal perspective? I've been thinking about this just in the vein of some stuff I've been thinking about for my lab work of cheaper ways to take photosynthetic physiological measurements from plants, where that gives you sort of an active readout into what a plant is doing. It gets you into sort of that temporal. We can see this actively changing. We can see the amount of carbon dioxide entering a plant, the amount of water vapor leaving it actively in a way that kind of makes a plant an agent in the way we can think of some things.
Yeah, I mean, I love this description and kind of, there is a historic thing where people didn't think, oh, are plants alive?
Yeah.
And then you can go to something and take someone's pulse. What is the equivalent of taking pulse? Which, I mean, and there is, you just measure the fluxes of gases coming in and out. I love this as a description and as a problem challenge, because I think it sets the stage for, independent of how you're thinking about the solutions, there is a framing here that's really powerful. And often enough, when The Secret Life of Plants came out, have you guys seen that, BBC? Yes. Okay. Secret Life of Plants is, I think, Attenborough's best film, I would say, in my mind. And he does something, and then if you've never noticed it, it's also a book, BBC video. No, okay, Private Life of Plants. It's not secret. I think Private Life of Plants. Come on. I want to show you guys a 10-second slip. That was very technical that they were able to do, but it completely changed the game in terms of how people perceive plants at that time. And watch the whole scene. Anyway, you guys should watch this film, all of you. Okay, I'm about to. Now, I want to show you guys a particular scene which is associated with
no part of the Earth is more hostile to life than the frozen wastes around the poles. 850.
Okay, I can't find it, but I'll just show you this as a.
Which automaker?
Okay. All right. Everybody should watch Secret Life or The Private Life of Plants. What I wanted to show you all was to make that film and to answer these things like why were people not connected? They developed this, and there is a back story of how they shot that scene. It took 1.5 years to shoot the scene. For a year, it's a time lapse of 1.5 years in a growth of a forest. And the camera is actually moving over a period of 1.5 years just around a series of plants while the plants are growing. And lots of people had seen time lapses. and your frame of reference is moving, you perceive as if you're walking through this and you're ducking under the sets of trees that are growing around. And there is a second film in which they actually talk about how they made that film. And that one scene completely changed how people perceive plants. And it's just the time scale is different. So I mean, I love that as a description. And independent of specific sets of threads, it would be phenomenal if you anchor on that statement, recruit sets of people, anybody who's sort of interested. I think plants have always been kind of the other in biology in many ways. And it would be phenomenal from a point of view of, I mean, I would bin this in kind of an education meets climate space. So we had a conversation with Teach for All, which is the largest organization that teaches globally, has volunteers everywhere. Teach for France, Teach for India. These are all sub-organizations. And the big thing that they're struggling with is climate education. And so climate education would be a really valuable thread. But balancing it with what you want the message versus just empathy for plants, like that would actually be a phenomenal thread. Okay, so every class will do one or two projects, but I'm hoping that many of you have started building teams and everybody has access to Notion, I'm assuming, at this point. So start writing these ideas down. Have people written anything down already for others to look at here? Anybody? Yes. Is it on Notion? No. Yes. Oh, it's already there. Can Kevin and can you guys link the idea board here just one more time? I just want to show that to you all. So let's just go to the idea board for 1 second, because if we don't take these steps now, no form, where is it? Um, so, ta-da. So here is the idea board. Is this idea board for 2025, right?
Yeah.
Okay, so I think I'm already seeing certain sets of categories. LLMs, global health, this is phenomenal. And I think one thread to think a little is, say, let's just choose this. This is a great example. You kind of describe a little bit, and then you can start thinking a little bit about populating it and connecting it to some things in the past itself. So look at other idea boards itself. Yeah, I think one thing that would be useful trying to recruit, the more you write here, the better it will be in terms of people getting a sense of how much you've already thought about it per se. And then one important thing about idea boards is make them your own. So I'm going to remember your name at some point of time. Jack, yes. So if Jack has written a problem idea board, you're kind of in it, but you have another twist to it, like kind of I had my twist and I was just trying to share that. Add that to it, and then Jack will also see that. And kind of, it's not about, oh, one person has an idea and you're recruiting. That's not how it works. In projects, it's a little bit about having a conversation, and ideas lie in conversations. So it's perfectly valuable to say that, oh, the title is sufficient enough that this is an umbrella. And so try making broader titles and focus them on the problems, not the approach. But you can still then have approach, because you might want to recruit, like, for example, Debbie is a phenomenal person to then engage in this as a process to say that, it would actually be fantastic if we brought these sets of skills to the table. So you can write the skills required, but idea boards are not something that you can edit other people's ideas. They're not singular in any way, and that's where to a group that is collectively aggregating around certain sets of notions. Okay, so this is, I'm happy with this. Let's have a tenfold more. We should create far more ideas than you can work on. And important thing to remember is just actually list out what bothers you. So if you have certain sets of things that you might have worked on in the past, you can generate a seed here that you it's perfectly okay. But I think it just sets the pace for you to say, I'll be thinking about a lot of different things. And then if somebody else ends up working in that space, you can still follow them. You can still kind of get a sense. And this is also true for trying to create teams amongst everybody else that's here. Okay, I think we're going to switch now to what I wanted to cover on optics. Um, quick comment on, so now DVD works. So sorry, I had to rush in the end. I don't know how long you guys ended up staying after that. Another 15
Did you
minutes
make
or
it
so.
to the keynote?
Oh, I just made it. Yeah, it was just, I wish I had remembered, but it's only because of Kevin's bike. And Rico's bike, I could not bike. It was too complicated for me. It's but I remember somebody saying that you're gonna teach us unicycle. Was that you, Jack? No, okay, so I wanna first start with what is it called? Fixie. Let's start with Fixie before we move to unicycle. Actually, Fixie is necessary for unicycle.
Yeah, a
Right?
unicycle's a fixie with one fewer wheel.
Okay. So that's good. So I mean, that was the purpose. We'll kind of dive a little bit in optics now. Usually I do this as a much longer lecture, and Benedict, who's a friend of mine, so another person who's engaged in the class, he's visiting in a couple of weeks. So we'll do a much more detailed lab session around a whole bunch of other optical threads itself. But I just want to cover a few. I want to broaden out the message that I wanted to give. So how many, by the way, of you were there on Friday? So at least some of you know what happened. So it's important to make sure that people that couldn't make it, if you can tell them what actually happened. Same goes for everybody in the class. If you were not able to attend the Friday session, and the way to do that is to just document whatever you learned in that, post that in the Notion page as a description of what you saw. Was anybody able to actually finish an optical path? Remember we were drawing the input output, yes? No, that's okay. Whatever you have, show me the diagram of what you figured out so far collectively. There must be somebody who's drawn. Does anybody have the pictures of what you drew? Okay. Yeah, but anybody has anything in terms of what the optical path look like? Yeah, that's good. That's good. Yeah. Anybody online? Did anybody finish the optical path for that DVD?
Not that, Professor, but I have an exciting photo picture to show from my laptop, dismantling of laptop. Once we are done with this, I am excited to share that.
Okay, can you make a post on Notion or Discord just so that then I can connect?
Sure, I'll do that.
Yeah. No? Yeah. Anybody wants to see? So I think the purpose of this is now you have all the excuse to dive in deeper in that object. Once you're in any piece of object, then the goal is to kind of systematically hack it and systematically go after it and really try to tease apart all the sets of things. I mean, we do this in biology all the time. We find something really wonderful that just evokes certain kind of an emotion like coral. You don't need to know everything about it, but then you systematically hack it to say, oh, the color of coral is not from the coral. And then you go deeper and then you go deeper. And so treat a DVD as a coral and ask yourself a question: who's living inside it? Who's doing what? Where is it coming from? And I think this is an important aspect, is that otherwise you will not be able to borrow what sets of pieces and what sets of ideas are embedded in your own projects. Okay, so we're going to dive into optics a little bit, and I think credit to Benedict, but I'm going to use some framings, and we might go over certain sets of things in a lot more detail and go over certain sets of things. What just happened there? Okay, this is And how do we make this? Urvashi, I see your hand. Sorry, I
Hi,
didn't see
yeah.
that. Did you have a
Uh,
question?
and I had my hand up for the ideas when we were talking about those. So
I
it was
see. Okay. No,
right.
I think
Um,
I'll cover the ideas now next time. Every class,
okay.
if Kevin, you can remind me, every class will sort of do one or two ideas quickly.
Okay. Yeah.
Okay, so let's think about light and optics, and I think this is you can take 5 years of courses in optics and still not know anything, and that's actually true for all subjects. I'll give you a little bit of a hint and just a little more motivation that whenever you are now finding these sets of ideas to try to go deeper, and initially this is sort of the approach that I take is sometimes you need a very disciplined approach to study a topic, and sometimes you need an undisciplined approach to study a topic. This is an undisciplined approach to study a topic, is that you are only interested in it because you find it fascinating. A bunch of things were put together and how do they work? And then you go in and you start asking yourself a question. I mean, light is everywhere. It's important to think about. And one kind of a thread is many of you had brought the mouse. So did anybody hack the mouse, the optical mouse? I guess everybody got distracted with. So that's what an optical mouse. So now looking at that picture, can you figure out what might be going on? How do you, now you are given, you did the hack, now you get what you get. So first of all, can some of you see optical components? And a new strategy in this case, as compared to what we saw in the DVD player. What do you see? Can you decipher from that picture how an optical mouse works? Yeah.
The LED would be the emitter.
Yes. Yeah. 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 Yes. So now the question is, first of all, we have light coming down, it's coming on a surface. You can see that there is a lens in the system itself, right? There is a little imaging lens. Something really unusual about the design of the optical mouse here is notice how the optics is in the shapes themselves. Now they're totally three-dimensional parts, not just flat mirrors or curves or the optics and the part, the mold and the optics is one and the same. It's just pieces of plastic. For some reason, because this, you probably have lowered what resolution you actually need. You've lowered the quality, because remember, DVD was trying to detect 100 nanometer scale structures. Here, care about just relative motion. And so this is a very clever trick that your optical component can just be injection molded plastic. Now, another thing that's very clever about this is that you notice the sensors. And so now if it's taking, I mean, you can imagine, I don't actually know in this case, whether it's making an image. Is it truly in the surface? Or what might be going on in that sensor, for example? So you see that sensor and you want to detect movement. So how do you detect movement from that sensor? Is it obvious? Given a movie, yes.
So the surface would have some roughness.
Yes. And remember, mouse does not work on very smooth surfaces because it looks the same. Okay, so now let's go ahead. You have some roughness.
And so then the light would take different amounts of time to hit the sensor.
Mm-hmm.
And so you can kind of like take a snapshot
Mhm.
of the surface at any given time and then compare it
Mhm.
to at the next time.
Yeah, so you kind of relation function, or in technical terms, this is called optical flow. All insects, all of us, when we're moving around, how do you know when your head moves that actually this is the motion that's happened? When a bee flies, at such high speeds, how does it know where the bee is going? You're taking two images at two different time points, subtracting to find what is the vector that is a directional vector that will correlate one image at t0 and one image. And you do this with very consecutive image. And the purpose of all of this is the purpose of all of this is you can only do this in a scenario where all of this optics and the parts was cheap. So it was quite a surprise when an optical mouse came along, because you all remember how they made the mouse before? Do you all know?
It's a rolling ball.
Yes. How many of you actually have that rolling ball? Very few. And still, some of the CAD file, there is a version of that rolling ball that's survived, but it was a game changer immediately because, again, mechanical parts, no moving parts. No moving part means easy to make, very little wear and tear, and that's kind of another thing to be thinking about. So this was a game changer in terms of thinking about in the mouse industry per se. There's also actually a very clever chip that I'm talking about. That chip does that in CMOS. So that's why it's real time. There's no compute. So if you ever hack your optical mouse, go find the part. Then when you find the part, you can find a data sheet for it. Everybody knows how to find data sheets? Yes? No? So any electronic part you find, it has a code. And so if I go on, does anybody have their optical mouse? No. Is there an optical mouse lying around? Do people online know how to find data sheets? So I just go in here and say, this is important, data sheet, optical mouse chip. That's it, ANDS 4700, single chip USB optical mouse sensor. So I do data sheet, ADNS, let's do 2620. And this is important. All of you should know how to read data sheets, because data sheets are kind of the one thing you need to use that part. There is equivalent data sheet for optics, for electronics. You can go in, you can say, I found this part. You can pick out to say, oh, here are the sets of pins that I need. So oscillator input, oscillator output, serial port, clock, shutter, ground, power, and some reference. And so interesting that now this is encoded. But what's really valuable about data sheets in society, we should have data sheets for everything, because this is all you need how to use this part. So when you're going to be hacking around and you'll find all kinds of things, it's not very useful unless you can really dig in. So, you know, it says, let's see, it's based on an optical navigation technology which measures change in position by optically acquiring sequential surface images, determining the direction and magnitude of movement. This is what we just talked about. It's kind of funny that they call it navigation technology. So it's kind of saying something along the lines of microscopic surface images. And immediately I'm thinking, oh, can I hack this to make a digital microscope? That would be a fun thing to do, right? So now I don't want just the direction vector. On actually the images, and I want to figure out if I swap the lens. So suddenly that sort of leads to a weekend hacking project. One important thing about a data sheet is it always gives you exactly one description of how to use it. So all the CAD files, everything that's in place, for example, this is one instance of how it can be used. And they're very extensive. So you go in, it'll teach you everything to know. And there are the images actually. And it's funny, I'd never seen them before, but so white paper, manila folder, and a test chart, and this gives you the resolution itself. And you might say white paper should have no contrast, but as you said about roughness, there is enough contrast. And if there is enough contrast, then you can actually determine the distance per se. Okay, so this is the undisciplined approach. You have to actually dig in the details. Like suddenly, I don't know, am I learning optics? Am I learning electronics? I'm just trying to figure out how does this object work. But you have to sort of dig into some of this by yourself. Okay, so optics is fun in a funny way, is because every time you open your eyes, you are forced to look through this object. And I was having this discussion with Benedict, and we were just arguing about this. How good is our eye? You guys think? How many people think it's just such an amazing optical lens? I'm talking about the optical lens in your eye. How good is it? How many people think it's a terrible lens? Kevin and I think. Anybody else terrible? It's all in our brain. There's a ton of aberrations that if you were to design it, you would. And it teaches you a very important that's happening. It's called computational imaging. What people realized was hardware and software was having this competition, and majority of optical products in the last 5 to 10 years compensate in software what you would pay a ton of price in hardware. So to a sense, why is it that cell phone pictures look as good as SLR? Kind of, they're getting there. SLRs. That's not because the optics has gotten any better, but it's because compute has gotten so cheap that in real time, and again, it's a strategy. It's often a way of thinking about, can I actually implement something in software that was going to. So our eye is a classic example of computational, what is called computational photography. That's where it started. And then later on, it's gone into microscopes. Yes.
Yeah, just like in reality, the lens in our eye image is upside down.
Mhm.
So, but because our brain and the soft computing is able to compensate for that, like we know in reality, like things aren't upside down.
Mhm.
Like that's just to demonstrate the power in which our brain.
Which is insane to just think about for a second. Like, what if, has anybody done this test? There is a test that you can do on a bike. If you take a bike and you put a gear in the handle of the bike, that if you turn, then I think the bike goes right.
It turns right.
If you turn right, the bike goes left, and if you turn left, the bike goes right. And with that, you get this thing, and then no matter how good you are at riding a bike, you can't learn. And a month later, you can, but then you cannot ride a normal bike. And so kind of there is this scenario, and I think I'm trying to remember, is there an equivalent version of the eye?
There's a special
That flips the glasses and your brain flips it back. Yes. Yeah. Don't do that. Because what if it doesn't? I mean, what is the guarantee? Do you get I don't guarantee, so please don't do that. I love this photo, and this is the first depiction, by the way, of glasses ever worn by a human. So they've been around for a long while. Part of much of everything that we actually do. And I think, this is an important paradigm around, we'll talk about fiber optics in a little bit, but just hacking through lots of things. I mean, you guys started with just one of the objects. So throughout the class, although I'm not going to ask you to bring it, what I would like, if you have an hour or two free at any point of time, go hack an object. So, explain what's happening currently in how sets of optics are implemented. I mean, we've had lots of sets of discussions around 3D scanners. Some time ago, 3D scanners were insanely complex and very, very expensive. And now every time you do, I mean, most of you on your phone have probably used this face detection that allows you to unlock your phone. That object is making a 3D representation of your face. Added in a single chip, super cheap. And then you can say, oh, why can't I use certain things like that to immediately scan all the coral under the ocean? And so you are sitting on this massive sets of tools and technologies that have been created for all kinds of things. And this was done for safety and security. I don't know if people have come up with fooling Face ID as yet or not, but it's important to understand. Guess, how does it know it's you? Anybody online? The question
Manu, there's
is,
a question in the chat. Yeah.
oh, go ahead. I am gonna unshare. Yes. I am looking at the question in the chat. What are the applications of the optical mouse? The optical mouse is to tell you which directions you're going, and I'm actually curious of what else would you use the mouse for? And I'll tell you guys a really cool project that 3-4 years ago, one of the class implemented. So, since you brought this up, application of an optical mouse, this team was focused on conflicts between humans and animals. It's a huge issue with elephants, and this was 2020. And I have to say, 2020 was a while ago. It's my favorite project of all time implemented in the Frugal Science class. And you're seeing an elephant and you're
Hi
seeing
everyone. This video is all about our project for BioE 271, the global frugal science course offered by Manu Prakash and group at Stan.
the question was, could you tell farmers were fighting elephants in South India? And they are still fighting, because elephants come in and destroy your entire crop and hurt people, and elephants don't know, they see food, and then the next day when you wake up, you see everything is destroyed, and then you go and hurt animals, and then people start putting traps for animals, and elephants get trapped, they die. The idea was an elephant coming from very, very far away. Around that time, there was a paper that had come out that elephants use seismic waves to talk across miles, 10, 20 miles. So we know that they are able to sense this, and they are generating these waves. And the question is, could you detect? And I mean, you guys should all watch the videos, and it's an incredible project. But the thing that I want to show you guys of what they built is this very clever system.
Shines on this piece of rough translucent plastic, the many rough features on the plastic surface act as monochromatic coherent light sources. These millions of light sources interfere on any screen that interfaces with this beam.
You can see the mouse.
And something called spectral interference pattern is a result. These patterns are basically random dark spots on a surface.
And
To the device output.
I'll let you guys see this, but
So
they
we could figure out
actually
how much of
built
the input
a
is
seismograph,
actually being
an
recorded by the
incredibly
device.
sensitive seismographs are things that measure
There
vibration
are some other hitches
of
in addressing.
and then
Instead
now
of
actually the
recording
project has
from
continued. There
us,
is a
we would
version,
like
Subir and Nish, and there is another new version now in which you just put this seismograph as a sensor. You can measure number going by, but from the signatures are so sensitive that you can actually tell from the spectrogram which car it was. You can tell elephants, you can tell all kinds of animals, as long as there is vibrations that go in through the ground. And kind of one of the goal and ideas around this is that it's done in a context of none of this would be possible without the optical mouse, because optical mouse is insensitive to these delta functions in the change. And the other trick, why was it so big? Can anybody tell me? Like the object, you saw the PVC pipe. Some of you will figure it out. Why was the object that we just saw like a big long tube?
It amplifies the vibration.
It amplifies the vibrations. It's an optical lever, because a small angle change in anything that's vibrating can actually be a large change on the other side. So any sets of vibrations can be amplified, very much like we amplify. So I don't know if Mohammed, if this answers your question. The optical mouse was not designed to find elephants, but that's the whole point of the class, is that you can take, frankly, you can take any two words in the English language and find a link between them. And that's a good project. Okay, where were we? Anybody wants to say how a face scanner works? So homework assignment, I'm going to leave that to you guys. Figure out how a face scanner works. And I will actually ask you guys. So this is, I have to start putting you guys on the spot. So this is an assignment, homework assignment. How does a face scanner work? Bonus points if you can hack a face scanner and bring it to class and see if you can get data, not from a face, but from any object you put in. That would actually be super cool. Okay, so I think the purpose of all of this, in some sense, is thinking a little bit about the remarkable capacity of these tools. And all I am trying to do is to give you kind of a little bit of a motivation to say that, yes, because these sets of scenarios are so remarkable, you should spend time thinking about some of these carefully. Another one which we haven't as yet talked about, but I'll give you a little bit of a hint, is worthwhile, is some of you have seen LIGO. You've all heard about LIGO. LIGO only works because of a really clever optical trick called interference. And now when you say, if you want to know how far something is or measure distances, one of the most precise method that we have is actually just using light. And we'll dive into interference in a little bit. But one thread to start with is actually, let's see if I have yeah, this is the picture I wanted to show you. So this is, okay. How do we know the moon is? If you were just born, you have what you have, you're not allowed to read a book, and you say, tonight we're going to figure out how far the moon is. What can we do? I gave you a hint.
Wait for an eclipse.
Wait for an eclipse. Okay, so let me think a little bit about it. If you wait for an eclipse, I'm assuming from geometry you can figure out how far. I think eclipse, I could figure out how big the Earth is. Is that sufficient? No, you need more data, right?
Yeah, you can
Or
find
is an eclipse enough to
you can
tell
find
how
the size.
because an eclipse, it's relative. Yeah, it's a little bit of a tricky thing of how to figure out the distance. So one factor around, yeah.
Really big laser, I don't know how.
Yeah, laser is good. Yeah, sorry. If the question was not clear, we're doing it tonight. So you have whatever you have. You have a big laser. Yes, absolutely. So you shine a big laser at it and something comes back and you could measure certain kind of things. You could measure time of flight sensors. Time of flight are there now. They're incredibly good. And actually in astronomy, lots of big lasers are used to back calculate some of the refractive sides of the story, all the kind of autocorrections. I didn't know this, but it actually also turns out people have placed mirrors on the moon. So there are some very specific locations on the moon that there are mirrors that you can target a laser and get a signal back. And one of the threads around this is interferometry. I mean, we'll talk about interferometry in general in context of distances. Let's actually kind of think a little bit about this in a way of, so, very simply put, if you think of light as waves, just, there is an emitter, there is an oscillator, is generating some kind of an oscillatory field. If it's generating an oscillatory field, you traveling field. So there is a certain wavelength, which is, we are going to use the word wavelength all the time for light. That's just the distances between different troughs or different peaks. Now there is a certain aspect associated that I'm calling it a sine wave. It's a good description of what's happening with the amplitude as something is traveling. And then there is a phase associated with it, which is really also just this is not standing, you can see that the peak travels. And so there is a phase associated with these sets of things traveling. Color is primarily just that wavelength. So this is kind of a review, but I want to get to interferometry using something like this. Now you can think about phase. Although these two lights are exactly the same, do you see a difference between them? One of them is what we call phase shifted. Phase shifted is just a displacement between one versus the other, right? You see that peak is at a different point. Now, we use this in microscopy in a very clever way and in interferometry in a very clever way. So the way we do this in microscopy is sometimes in microscopy, you measure the absorption of light. That's the classic transmission microscopy, right? So that's why when you stain a sample, that absorbs more light, and so you get a contrast. But there is also label-free imaging in which you don't stain anything. How many of you have used the phase contrast feature in a microscope? Anybody else? Some of you? So
DIC.
DIC, exactly. Differential interference contrast. There's literally a Nobel Prize for DIC, because in the old times, we were looking at dead stuff. You can stain that. There's tons of Nobel Prizes for stains, including Golgi, the Golgi stain. But Zirkin came along and he had this idea that he wanted to just use no stains, see live things, but still have contrast. And the trick that he came up with is that if you look at a cell, there is a beam of light that passes the cell, and it doesn't have retardance in the sense that the phase travels at the same speed. So everybody knows speed of light is dependent on refractive index. And does it slow down or speed up in glass, for example, or media? Slow down, right? It slows down. So now that second beam that's passing through is slowed down in the cytoplasm. When it passed through in the nucleus, it would have another unique, so it might slow down further. Now, how do we see? Our eyes don't detect phase. We're not sensitive to phase. It's too fast. How do we convert that signal into making it sensitive to this retardance? And the idea comes from interference. You take the two signals and you add them, which is exactly what LIGO does. So if you watch those two beams came and we added them up. You can see you shoot a beam. There is a beam splitter right there. It sends the beam. And if the distances between these two arms were exactly the same, the two waves will come and add up. And if they add up, what would happen? There would be no change. They would still look the same, right? So that would be constructive. But if I now shifted it by 90 degrees, when the peak and the valley coincide, so if I took this branch right here and I increased it by half the wavelength of light, like wavelength of light can be 100 nanometers. Now I increase it by, say, 50 nanometers or something. This second beam that will come, this peaks will not be together. It will be phase shifted. When phase shifted, you add one object into another object that's completely phase shifted. You get darkness. And so many of the Newton rings, everybody's seen Newton rings, right? No? If you take two glass slides and you put them together, you start seeing these rings. Those rings are actually phase shifted because in the end, the gaps are such that you get interference. And so this interference will give you, so now suddenly you can make a sensor that is in the ballpark of wavelengths of light. And interference, these interferometers, I mean, this literally, the 4-kilometer interferometer is a real object. I mean, it's insane to think about the fact that we could see bending in space-time. Everybody saw the result, I'm assuming, for LIGO, right? Yes, no, it was in the news everywhere. How many people know what LIGO is? Okay, not many people know what LIGO is. All right, so now I have to digress. This is important. This is kind of few things as humanity that we have to be proud of. LIGO, not sardines. LIGO is the world's largest interferometer that was used to prove that when all kinds of things happen in our space-time, that you can actually see distances that we perceive are actually not stationary. There can be a ripple in space-time, and a ripple in space-time can be seen. And it is one of the most amazing things from optical instruments point of view. So to make something like this work, so if you guys spend some time essentially looking at the kind of instruments, this is not frugal science. It costs a lot of money. But very important to think about. The ideas are still there. So they have these mirrors. Now, the problem is you are on Earth, and Earth is shaking all the time. So how are you going to measure something like a ripple in space-time when you are already on no solid footing? So all of these systems are actually built on flexures. So this thing, massive, heavy mirror on a very tiny thread. So it decouples from thermals, it decouples from everything. It's inside in tubes, then they pump vacuum in these kilometer-long tubes to build these incredible optical structures that then cause, so although, this is at the end of that tunnel, this is that mirror, and it's the heaviest mirror. I just want to see a person for contrast. Yeah, so here is the person, and let's see if they have the hanger associated with it. So somewhere in there, and I remember when I was at MIT, because there was a lot of people working on LIGO, one PhD thesis used to be this one part in LIGO. Like they figured out this one particular thing in LIGO, that's one PhD. So it's like, I mean, hundreds of people working on just the vibration isolation, because you're trying to measure something so sensitive to remove that. But there is lots of principles that are valuable to learn. And in that scenario, it's, interference has become a very powerful, and it's also a very cost-effective way to make extremely sensitive measurements. And frankly, interference could have all kinds of products and applications, and it hasn't really been utilized in many of our classical products to think about. That's why I'm spending so much time. Microscopy is a little bit more obvious, but interference is a little obvious, and it's important to think about how you would actually, say, build and design scenarios. So this is what I wanted to show you guys. So that's just the hanging mechanism of the mirrors itself. So there is the test mass, then there's the second, and it is all run through these sort of coils. And we will talk about flexures quite a lot later on. Remember, many of you saw the voice coil in the DVD was on these wires. Same idea. Flexures, they allow you to give atomic scale smooth motion for a very little price. But in this case, they're kind of hanging upside down. Okay, so, LIGO is basically the implementation of this at a massive scale. And one of the important things that ends up happening in something like this is it's for one of the sessions when we do microscopy, we'll also try bringing a DIC system, and then I'll show you guys kind of how it's implemented on a normal microscope, because then you'll understand. There are other tricks to it too. In the microscopy context, I had said that what if you could combine these things? But now there is a problem. You see, how do I combine them when they are separated? Right? So I need to do something to be able to combine this light. I have to combine this light with the reference light. Mirrors, that would be one. And so That's why all current DIC implementations use what is called a Walston prism. And so what put a reference shift to begin with, and then another prism to cancel the reference shift. But when there is nothing in there, the cancellation is exactly equal, right? So I put a prism here, like a triangular object here, that's thin here and thick here. And so you've generated a reference shift. The retardance has changed by this much distance. If I was a little bit further, that just cancels out and everybody is back in phase again. But if you have an object here, that messes up with that cancellation, and that's what then leads to you getting a contrast. So the next time you go to your DIC, try removing one of the prisms and you'll see the whole thing falls apart. So it's valuable to kind of think about that there is a lot of tricks hidden in most of these sets of objects.
You can change the
That's correct.
from like 0 to 90.
Yeah,
Is it
and
0
you
to
can
90?
move, yeah, there is a little knob on that prism. And then of course, you do this in a particular polarization itself. So there's two tricks, and just for that trick, 2 prisms and 2 polarizers won a Nobel Prize. Because again, just its impact was really remarkable because it allowed people to do certain things that nobody would have thought about. So very simple ideas can lead to it, you know, that was the first time people actually saw a spindle. So inside, before, people had seen all of these sets of things in dead systems like onions that they would stain, but nobody had actually seen a spindle live. So lots of objects were made possible. And again, it would actually be interesting to say, what is the simplest implementation of interference microscopy? In Foldscope, we do a trick. It's called which we use angle light to generate these contrasts. There are actually other tricks that you can use to generate contrasts, but the components and parts to generate true interference microscopy is actually still open. Okay, so what else do I want to say? Maybe let's spend a few minutes on, I am assuming all of you have made pinhole cameras. Yeah, this is another thing that you should think a little bit about. Spend some time. Why does a pinhole camera actually make an image? One important thing to think about is, although we are talking about curved fronts, when you're far away, we will also talk about flat fronts, and these flat fronts are an approximation. This is the primary reason ray optics even works. Otherwise, ray optics should not work because, you know, I should be dealing with all of these curved fronts, but often enough, certain distance, these become flat, so you can represent a ray of light just as a line, and then you can just do a ton of really amazing geometry. And I'll say a few of those sets of things in some sense. So, you know, you can have a scenario where a plane front can pass through a defect. As I said, that has a specific refractive index. If it has a specific refractive index, this wavefront will change. One way to actually look is, we were just talking about this, for example, if you just focus on a laser pointer and a laser pointer points to this rough surface, the rough surface will cause what is called a speckle pattern, right? So speckles are these sets of scenarios, and that arises from the fact that the beam, when it's bouncing off of a certain amount of an area, it's actually bouncing in many, many different directions. And you can use that in many clever ways. And one of the clever things that I've seen this play out is there is an optical trick to use speckle patterns and scattering. So what is happening here is, when you take light that's coming, you can see this is a simulation of lights coming as wavefronts. And I'm just putting some inclusions in there. And of course, all of these waves then will start interacting with each other, and you get this, a little bit of this random pattern. When I was in grad school, one of the my lab, a few sets of people in the lab came up with an idea of using speckles as a lock and key mechanism. And so it's a really bizarre idea of using optics to actually encode a cryptographic function. And the idea is very, very simple to explain. The problem with lock and key is if I give you the key, it's super simple to copy it, right? So why do we believe that a key is, I mean, literally, I pay $2 and you can literally buy a copy machine that copies keys. Don't do that. It's illegal, it's against the law, but it's possible. So now can you imagine a key that cannot be copied? A physical key, I should be able to give you. When I give it to you, you can unlock something, but then when I take it back, can we imagine a physical object that can be shared amongst each other, has to be physical, but cannot be replicated? Anybody wants to guess?
Qubit, right?
A physical object, qubits, cannot be replicated, but the moment I give it to you, they get decoherent and they will get lost. So a very bad key, because by the time you reach home, you've already lost it. So, but are there objects that you know that you can hold in your hand but cannot replicate? But you can make them. So the idea was very simple. And again, classic notion of frugal science. You take glue and you put in it 1 micron glass beads. So it's a 3D volume. I just took super glue or any kind of glue, and I randomly put glass beads. Now those glass beads will land in any random position. These are 1 micron, but I make a big chunk of those. So, maybe like a centimeter cube. So it has now built in them in that perfect locations. I can pass that to you. We have no technology that can replicate that exact arrangement. So now the trick was just that you can take this object as an optical key. There's a particular angle that if you shine light because of me scattering, now you cannot replicate it because the output signal that will come out of this is the exact interaction of light in all of these sets of passes. Scattering, the light is actually bouncing inside this like a billiard ball, and it comes out in a particular way. So we have no technology currently, no 3D printer can actually do this, because if you do the calculation, if you were to make this at a micron by micron scale, it'll take a couple of years, and we can't even do that. As an object, it's trivial to make. It costs 2 cents to make, just a tiny bit of glass beads and thing. But it has a particular signal. And if the speckle signal is exactly that, then you open the door. And so there are 2 things you need to know. You need to know the exact angle you shine the light, and you need to have this physical object. And then it became, just this alone was a science paper. It was called optical one-way functions. But the clever trick here is this notion that you can make something very sophisticated out of nothing that can never be replicated. And it became, and now there's all kinds of other ideas related to this notion. If you think about that, if you need a system in which unique objects need to be made. So for example, medicine, it's a huge issue right now. In medicine, there is massive number of fake drugs in the market. I mean, some people say between 30 to 40% in many developing countries, the drugs that people are taking are fake. So now you need some kind of a cryptographic thing that manufacturer makes it, you can put it, you need to verify it very quickly, but nobody else should be able to replicate it. So right now people have this aluminum foil and all kinds of fancy print, but all the machines exist for that print. So packaging is not sufficient. In the old days, you didn't even used to package, but most medicine, and especially medicine in many developing markets, are packaged because the packaging is what you trust. So now can you imagine, can you imagine some way if you were to solve this problem? How would you solve this problem? What would you want to make that's easy to make, but only by you? How do you verify?
Professor, I
Manas,
had a question
go ahead.
before
Yes.
the glass beads. How reusable are they? I mean, when you're exchanging, I'm assuming wouldn't they get affected by all sorts of like environmental factors? I mean,
So in that case, all the glass beads are embedded in a solid piece of epoxy. So then it's done. Everything is actually inside. Now you have a very important practical question. Why are we not using optical keys? There is a flaw in this idea, which is it is also sensitive to surface roughness. So then what you have to do is just before you go open your house, you need to polish the surface a little bit so that little dent will completely change the scattering. So that's why we don't have. So it's not the beads. The beads are there forever. It's easy, but it's sensitive. It's very sensitive to surface roughness. Any ideas? How would you solve the medicine crisis? This is just thinking out loud. It's not as if there is a solution that exists to this. This is an open problem, by the way. I've been thinking about it for a while. Two groups that have come up with. So first of all, Foldscope is used to detect fake medicine because a group came up with this notion that many of the medicines that we use are actually encapsulated. They are not just powdered, they are emulsions that are then made into pills. And so if you break open an aspirin and put it under a Foldscope, you can actually see if it's a very particular size of an emulsion because it was in the process. Medication is very difficult for something else because most fake medicines are just powders put together. But anybody has a brilliant idea of how would you crack this problem? Okay, think about it.
Do you think going after the packaging or the actual medicine itself?
We have all our freedom. We could imagine anything. I think the packaging has been one of the key places that people have tried to. I mean, so if I open up here, you'll see fake medicine packaging.
Manu, I think a solution for this exists for books as well. They use these optical kinds of stickers only.
RFID, you mean? Is
Uh,
that what you meant? No.
no, it's not RFID, but it's like very shiny stickers which they put on book covers and all, which prove that the book
Hologram.
is from the specific publisher or.
Yeah. Is one place. But the unfortunate reality is even holographic printers actually exist now. So holography is a really good idea because in the old times, I don't know if some of you know, our notes have the same problem. And many of our currency has holographic things, and there's very clever optical tricks in how to make holograms. But counterfeit is a type of a business that if you keep moving the line, I mean, of course, everybody knows there's also counterfeit money too. It's not, but eventually you have to keep moving whatever technology that you come up with that acts as this scenario of a barrier will eventually get in hands of other sets of actors as well. Yes.
What if you had like some really simple diagnostic test that you like put the pill in water with and it's a perfect pH.
Yes, so I'm gonna show you.
Or gold when it hits that exact pH of the medicine that could be.
So this became, okay, no, I don't need a fentanyl test. Fake drugs, paper, chemical strips. This was a project that actually a phenomenal thread on utilizing now this to with okay, Notre Dame. They're called pads. Literally exactly what you said. You take this stripe is just a piece of paper. It has embedded chemicals in it. You take whatever you're trying to test and you dissolve it and you dip, and you get 10, 15 independent colorimetric reactions. And a signature, the optical signature of what you would see. Sorry, I'm not sharing my screen. So I just want to show you what Danny just came up with, I wish you'd come up with just 10 years. You're only 10 years late. But that's brilliant. That is what I want you to do is you have to think on your feet. And this really has become one of the important solutions. It doesn't have everything, but one of the aspects of this is a card for specific medicine, and you really do a test. What it also allows to do is certain kinds of things where adulterants could also be accounted for, because there might be certain all the time in sets of systems, adulterants are actually used. And it's a very general idea. Because it's a general idea, you get a scenario of thinking about, you can actually keep making them for different sets of tests per se. There is a limited repertoire of how many things can be color. So there is another aspect of, oh, can I use computational imaging? I take a photograph of this and from that back calculate, because a person at the counter or a person like a normal human being who's doing this test wouldn't know what signature I'm supposed to see. So there is an app associated with it. But this has been a very important scenario from being able to do explicit test. You know, you can't do that for every pill per se, but on the other hand, so these so another homework assignment. Let's see if by Friday somebody comes up with a new way on the counterfeit side of that story. Yes.
Is it like 10, 15 different like
Compounds.
color
That's
compounds?
correct.
So it's like a unique ID because
For that particular drug. That's correct. Yeah. So what they do is they just look at, there's lots of compounds that do colorimetric assays, and the card can be designed position because most drugs are multi-chemicals to begin with. So you have enough of a combinatorial chemistry to play with. And you can also make a card that is for all generic drugs, for example, that, oh, only one of the lines should light up. And if somebody's putting urea, you can have separate lines specifically for adulterants that people commonly add, right? If somebody's just adding sugar, it's a very common to reduce the price, you would see, wait a second, this thing has sugar. And this is super easy to make. If, you know, in diagnostics and other threads, if we go down the direction of RDTs, and just for fun, we could literally actually make this super, super easy. All the protocols, this is just wax printed on lines to make sure things move in one lateral line and these lines don't talk to each other. But other than that, okay, how did we get here? So I think beans, counterfeits, yes. And that leads to this notion of thinking a little bit about, you know, I think the point I want to come across is it's important. We can have all the fundamental knowledge in the world. If you're not thinking, you're not going to arrive at the unusual things that actually solve problems. So the lesson for today is undisciplined approach to learning, that you know everything is connected to everything else and effectively, but you cannot appreciate it until you also dive deeper. So I think this is kind of the thing that although I wish we had all the time in the world that we could really do deep dives in every possible field, I'm just going to give you teasers so that you feel a desire to do a deep dive in some of these fields, specifically for the projects that you actually choose. So like if it turns out that this approach of bringing symbionts works, then the deep dive will be in the material science of the world, right? That's kind of the thing that you say, so much is known about this. For me to find the right material, I'm just going to map. That's going to be on the teams. And I know that not everybody can deep dive in all possible topics, but the project that you choose, I am expecting that you will go really deeply on having the time you spend to understand that field. So if the core solution arises from this material or a core solution arises from optics, then you need the tricks of the trade. Like you get to do, it's a little bit like abstract painting. You allowed to do abstract painting when you have mastered the classic fine arts. Because otherwise, I always walk around and say, I could have done that. And, it's built in, but you don't understand the subtlety of these types of things. So what you're seeing in many of these solutions that are implemented arise from the classical understanding of things. And it's important to balance the two. So in the core portion of the choose a field. And then if you chose optics, or you chose gas sensing, for example, like, if I'm thinking out loud on CO2 side of the story, and somebody chose microfluidics, and I can clearly see, people are now coming together as a team in which they've chosen a specific area to do a deep dive in. Okay, we are out of time. We're going to continue a little bit more on optics. I'm in town. Do people like the labs, by the way? What do we want to do? Do we want to continue the labs? Yes? Okay, so we're going to do microscopy as a lab this time. Let's bring out some of our microscopy tools. We might try building one of the squids, Kevin. So let's get all the parts, the same instrument that we took. Enrico knows where it is. Not the big assembled squid, but the other squid. Yeah, and then we will optical trains. We will do some telescopes. Let's mess around with those telescopes itself. And then we can do maybe polarization and fluorescence so that we can do the cubes. I'll show you the cube setup. So maybe Enrico and Kevin, if you guys talk a little bit, and we have to anyway organize some stuff. So we'll pick up on Wednesday. Everybody should have some vague idea want to do. Oh, wait a second. Before people leave, Shivam, I know you're eager to show something.
Yeah. That I think you told me to share it in the Notion. If you want, I can show it here as well and put it on the Notion. But I had a further question, Professor.
Okay, open mic. You want to take and share your screen?
Sure. I can do that as well. Meanwhile, I'll just ask the question and also try to.
Yeah, go ahead. What's your question?
So, Professor, I had a question. So when I opened my laptop, there was a
You can just call me Manu.
Okay. Manu,
Yes.
I opened the laptop and in one portion, I reach, that's where my engineer gets down in my life. So I saw a screen where it says don't touch. And there was this one tape which says don't touch. So once I tried to open lithium batteries also, and then it said
Yes. Oh, you opened a laptop and it had a sign that said do not touch.
Do not touch.
Yes.
So in general, my question, until I would not know until I open, I don't know what to be opened or what what
That's
not to be.
correct.
Is there a list or is there a way of general rule
Safety, some safety advice. Yes.
Yeah. So that
First of all,
sorry.
I get your question completely. There are two types of kind of messing around with objects. First is that you have a desire, a very strong desire that you remain functional after your learning experience. So any object that you choose, make that decision early on. Because if I open something up, I have made the decision that I'm willing to sacrifice for the value of learning. There is also a term called dumpster diving. How many of you have heard that term? How many of you do dumpster diving? At least some of you do dumpster diving for food, for all kinds of things. I found all kinds of really amazing cheese. I always do it with my friends. I try to teach, and I'm not happy with how they react to it, and something wrong in society, I feel. There is a ton of objects that you find just littered around that have incredible learning value. They are not lost in any way and form. And again, none of it would be recycled to begin with as well. The more you can learn, the better. But it's important to have safety. So around batteries, it's incredibly important to make sure you always wear gloves, always wear safety glasses. Lithium and lead batteries are quite dangerous. Lead recycling is actually a problem that we will pick up. Currently in South Asia, massive number of lead batteries are recycled, and they're recycled with no safety instructions. And because of that, lead is leaching into the soil. And currently the highest blood level for lead, which is incredibly toxic in children, exists in. And so in some sense, the recycling industry itself we need to recycle, But at that same time, we need to build the kind of safety standards that don't cause more problems. So currently, there is a massive lead poisoning as an issue because there are no good tests for lead and the lead leaks out. Lithium batteries explode. It kind of a shame. And I think, again, we're building kind of this electric future of our world, but we solve the problem of the kind of environmental damage many of the batteries cause. So just on a personal basis, make sure you never puncture a battery. I remember as a kid, I used to open up the alkaline batteries and get the capacitor out of it. There's like this beautiful thing inside. And, later on in life, you learn, we used to extract mercury out of thermometers. Very bad idea. Don't do that. It was like, oh, no, you see all these broken thermometer and there's this one shiny thing. Of course, you're going to try to extract it. So I think be smart about it. Okay, Shivam, now go ahead. I'm seeing a picture of a beautiful laptop.
Yeah, and also, Professor, I ended up opening that screen also. If you give me a second, I can share that as
Yeah,
well.
I want to
I
see.
ended up like going to
Can you
the.
try to put it back together after or not yet?
So I
Or
have the
it's a
one
lost
which I'm
cause?
talking on the laptop that I opened
Yes.
and I put it back. So I'm hopeful like I can put that back as well.
Yeah. So by the way, there is a methodology to it. You can put together on your table an organizational structure. So people that do this properly, you have to organize all the screws. There is a coding scheme. You take notes along the way. So do it in a structure. By the way, class is over. Now this is open mic. So if you want to hang out, you hang out. But if you have to leave, you have to leave. I understand that. Organize your space when you're trying to do this. And it's best done that you create a very specific environment in how you're organizing the tools.
I see.
Okay, any other open mic threads? Anybody from here? Are you feeling nervous about your project? You have a vague idea? Does everybody have some vague ideas in which they're going? You guys could do a social hour by yourself, like all get together at 5 o'clock in Tresidder, wherever, like try to figure out a way that there is a conversation happening between people. Otherwise, it's going to be very hard to build teams. So, and again, it's also important. I don't want just Stanford teams and then the broader cohort. It's actually really important that you integrate. So, Coral team needs to find a partner that lives by the ocean somewhere where bleaching happens.
Or someone was texting, I think.
Next to the ocean.
See,
go
sorry.
ahead. No, go
So if
ahead,
you
Shivam.
So in this screen, I was always fascinated, like, how this LED, if you see, I've opened the LED as well.
Backlit. Yes.
Yes. So I did not know like how exactly the thing, because for me, TB is like that big thing, like,
Yeah. I remember the depth, the
Yes.
electron
I was
gun.
always fascinated, especially the Apple laptops, very small, thin. So I was like,
Yeah.
where is the tube thing? Where will it
Yeah.
be put it? So
Yeah.
today this somehow accidentally, because it was broken on site. So I saw I could even open this. So I just ended up opening, and this I all opened with a small one screwdriver and one knife.
Yeah.
So I could open
Is
with
this the one at the bottom, right? I can see. I mean, one of the very cool things, I'll show you guys a patent around this. So if you unshare your screen for a second, I want to show you guys the patent for what is called back. You've all heard backlit screens. So this was the original patent. It's a very clever thing that all of the white that you're seeing on the screen, or just the pixels that you're controlling, are being backlit. And I don't know if some of you, in some of the old laptops, this used to be white. That's because this thing is backlit by something, but light is actually only on the periphery. And so that's the pattern that you can see, that there is this turning film. The light source is here at the bottom. Do you all see that light source? And all the light is bouncing through here, but then you have enough uniform lighting. So it's a very clever idea, how to get a uniform lighting in a very broad scale. And then the little white drawing pads we were using on the boat is a very similar. Backlit screens came much later. And in some sense, They really enhance the idea of some of these ultra thin displays. So another very valuable type of document to figure out is read patents. Just like data sheets, they're super useful in getting into the nitty-gritty, and there is a massive number of totally worthless patents, but there's some really good patents that trying to decipher and go backwards and reverse engineer. It's perfectly important for you to go dig in and know and find. Do you all know how to search and find patents? Yes, just Google patents and just search for a name, international patents. Patents are required to provide enough information that person skilled in the art should be able to replicate it. So by the act of filing a patent, people are sharing knowledge, and you should read it so you can also evade that patent sometime, and you're trying to do something else and say, okay, now this space is occupied. I need to do something like this, so maybe I need to come up with another idea to actually not be infringing. Okay, Manas, go ahead. Oh, Kevin's favorite patent. Is that the Lego patent?
Otis Boykin's resistor, like the resistor that we know today with the band, put it on the board. Yeah.
That is super cool. But it's the making of that resistor?
Like the packaging and the yeah, packaging.
Oh my goodness, I never thought of opening Otis's resistor. Ah, I love this. So there's all of this packed inside? Oh my goodness. Okay, I have to share. Sorry guys, this is too exciting. Look at this. In a tiny resistor that just looks like this tiny, I mean, I have to say, electronics and a resistor is just so artful. It's just that bands, it represents so much in society in some sense when you look at that. And we all learn you learn the code. What is
Black, brown, and then rainbow.
yeah, and but this is actually inside. I mean, I used to do this for capacitors, but didn't realize that resistors would have this. I guess it makes sense. In the volume, you have to pack so much resistance, and you need to make sure that that would happen in a scalable manner. Electrical resistor. Oh, that is fantastic. 1956. And again, this is this notion that when you solve a problem, then really scales. Way for patent inventions is by hand. So you see the value of drawing. Okay, maybe for the next class, people should share their favorite patents. Okay, please post your favorite patents on Discord. Yes. Oh, see you guys Wednesday. Again, 2 projects we will discuss. So if you want to recruit early, you should come prepared for that. Go ahead, Manas, and then Vaibhav.
Yeah, Professor, I just wanted to know your kind of opinion on this. This is something that I've been kind of thinking about. This is a problem.
Manas, can you introduce yourself so I remember who you are?
Hello, Professor. I'm Manas from Ashoka University.
Yes.
I met you last time when you gave your talk at Ashoka University on curiosity, and we kind of discussed we were kind of trying to work on a microscope at Ashoka. We were trying to replicate a moving 2-photon microscope. Yeah, so after that, Tushar kind of forced me to, not forced me, but introduced me to this class, and I was kind of hooked onto the idea.
I am glad you're here. Yes.
Yeah, so Professor, I had this kind of question on how to approach this problem. So I noticed in my previous volunteering that Alzheimer's or any sort of neurodegenerative diseases, like for example, Alzheimer's and Parkinson's primarily, the rates of diagnosis in urban versus rural areas are really bad. Of course, there is an issue of lack of awareness being one of the bigger things. But what I was wondering is there anyone who's been working on some sort of diagnosis tools, which is in the sense portable? Has anyone explored these areas?
That's a massive space. Almost all of diagnostics works in portable, low-cost diagnostics. We will do an entire class and lab sessions on diagnostics. So you just have to wait for a few more classes. We'll
Okay.
cover that. Yeah,
Got it.
yeah.
Thank
It's
you
an
so
entire field in itself. Vaibhav, go ahead.
Yeah, Manu, about the example of the glass pieces in the mirror, I wanted to ask from you, like, how is it not replicable once you, like, I assume it will be the reflection pattern. Once you shine any kind of light on it, the reflection pattern will be unique to that object. But
Yes.
like, as we can copy the holograms, which you mentioned, won't be able
Yes.
to copy the reflection pattern similarly. May not be able to make the exact cube with the glue, but match
Yeah, but
the.
if you can't make the exact glue, the speckle pattern will actually be different. And if the speckle pattern is different, then you end up with a totally different key. So it will not open the same door. So here's the paper. I'll share that with you. Kevin, can you post this online? It's just called Physical One-Way Functions.
Okay.
And the object is right here. So that's the 3D token leads inside a piece of glue. Okay, that's it. Yeah, it just shows. So yeah, take a look at the paper. Okay, Arth, go ahead.
Yeah, Manu, so I'm considering to make a hemodialysis machine, something that's maybe portable, which folks can take around and maybe perform that by themselves. I just wanted to quickly know the logistics of office hours with you and if there are
Yeah, I
any.
think Friday would be a good time, Earth. And I saw so many of your messages. I'm sorry we haven't been able to connect. I
Yeah.
am back from sea now. So this Friday, I will open up office hours for projects. Write a short description of the project and let's have anybody else who wanna just talk about hemodialysis.
Sure.
There's another dialysis idea that we've been thinking about. So this and in some sense also getting a sense of a good understanding of where the problem is. So,
Okay.
so kind of dig in, think a little bit about next class, I'll cover the Fred Park framework. So all of you will be asking for functional requirements. But for the discussion, so I'll do that on Wednesday. And on Friday, you should try to fill in. So we have a good sense of where the gap might exist in this space.
Sure. All right. I'll try to look up a little bit.
Yeah. Okay.
Yeah.
I'll see you guys all soon. I have to run. Oh, Shivam, did you have a question?
Yeah, one just clarification. Professor,
Yeah.
you mentioned about this method of reassembling and putting back. Could you tell me?
Yes, it's a website called Fixit. Uh,
iFixit.
iFixit. So go look at iFixit, and what's valuable is that fixers and they share all kinds of tricks in how to fix things.
All right.
Yeah,
Thank
and it has all kinds of tools. But it really is a phenomenal community. It's 65,000 devices, 100 million repairs. So if I type laptop here, it shows guides, step-by-step guides on how to fix things. It's also just interface and a community.
Thank you so much,
Okay,
Professor.
I gotta run.
All right. Thank you.
Bye, everyone.
Bye-bye.
Yes.